Bismillahirrahmanirrahim. Ladies and gentlemen, welcome once again. Surely your wait is about the summary of the previous lecture, so I will not disappoint you. I would like to start from the summary. As you know that in the previous lecture we talked about the fourth and final problem of the estimation. Fourth and final doesn't mean that there are no problem to the estimation. There are many other problems, but we are restricting ourselves to the fourth problem because if we keep on going, there may be some boredom, and you may say that we may be skipping some of the more important issues. The only you have to, the purpose of the course is to give you the basic insights into the issues. So if you remember, our discussion was specification bias, very critical issue, and we talked about that there may be two, 3 or 4 kind of specification bias. Over and under fitting of the model, very quickly going through, I would like to say that if you include some extra variable into the model, it becomes overfitting, and unfortunately if you exclude some of the important variable out of your model, this is called the underfitting. There were some we did a comparative analysis that which is more costly in sense of that it penalizes more to the researcher and which is less costly. Although I am avoiding this to suggest that overfitting is not too dangerous, but at the same time, if you remember, we saw that many of the problems do not appear when we overfit the model, and there are very, very dangerous consequences when the model is underfitting. Although we concentrated on only 2 of these problems, but there are other problems, and we will go through this problem at the end, that the measure of error. And that what happens if we measure our dependent variable, that is the y, with some of the mistaken, or you can say it is not correctly measured, and what happens to the x variables if they are not correctly measured. So in the our discussion was just limited to the formal method of detection this specification bias. Now I would like to start from the formal methods that will help us in detecting, and on the outset I should clear that now we are talking about the underfitting of the model. Overfitting of the model detection is very simply estimate the model, see whether your slope coefficients are significant. If they are significant, then you will have to include that variable. If they become insignificant, you can get rid of those variables. But now we are talking about the underfitting of the model and some other kinds of the model you will see later on. This is food for today. What we will be talking about? Formal measures, and the one is the Ramsey test, Durbin-Watson test, LM test. It is not the limit. There are many other tests, but don't worry, I am just concentrating on that are very famous and celebrated tests that all the you can say softwares has. Although you are knowing about this background of this very small background, I am not using the mathematics, and keep in mind whenever I make any of the claim, it has a mathematical, you can say, the support. Without any mathematical background I can't say anything, but I am avoiding this because nowadays there are software, and only with one click there will be the test of you can say the specification test. As you will go there will be number of tests, and you should come to know that whether your model is specified or not. I will be just giving you a very small insight into the test. The first formal method of detection is that the plotting of the omitted variable. Omitted variables are the plotting of the examination of residual. Now I would not like to repeat this. Keep in mind that we are talking about the detection of the specification bias, And we are not talking about now the overfitting of the model. This is underfitting. I may call it that omitted variable case. The first formal method is examination of residual. Residual, or you can say the error terms behavior, is very, very critical. If you know the assumption of the classical linear regression model, it assumes that the expected value of the ui hat should be equal to 0. What this means that the ui or the residual term have no systematic process. These are purely random. And if they have some systematic problem, it means the forces that are outside of our model are affecting our dependent variable in a systematic way. It may inflate the value of our dependent variable. It may understate the value of dependent variable. So what we want that the if we plot the residual that we get, we estimate the model, at the end we get the residual. Residual is simply the observed value minus the estimated value. When we plot all these residual, what is our objective? That these should be randomly scattered. And if they are randomly scattered, many of the problems are solved and we need not to go further. Although there are some further criteria, you can say this is the first major blood test. If your body pass this, your research pass this test, then there are some specific tests for this. Ultimately, you can say this is the first test. You can say it is the, as you go to the any of the OPD of any of the hospital, first of all, they check your blood pressure. And you can say this is the checking of the blood pressure. Since the previous lecture, I am talking about more the, you can say the medicine, because every one of us is facing and has exposure to such kind of thing. If I am going something else, you may understand, but the example maybe you can say the not as general as it should be. So the examination of the residual can be examined especially in cross-sectional data for model specification errors such as omission of an important variable or incorrect functional form. Two problems here. Incorrect functional form may be there. For example, your dependent variable should be simple. You did it the log of this. This is the wrong functional form. So the first thing, we plot the residual. For example, suppose, again we will be supposing that this is our true cost model. Y is the output, Y is the cost, and it depends on xi, the linear relationship with the output, xi square, the cubic relationship, and the quadratic relationship, and this is the cubic relationship. So we suppose that this is the model because we write the complete model, and you know we will be talking about underfitting. Now we will be assuming that we are excluding some of the variable. So this is, but a researcher fits the model. Now I am supposing that your name is Amna. Now we are more familiar. It is my random and it may hit the target. I am not sure about this. But this, the Amna comes with the model that this is the model. Rather than the true model, she estimated this model. That is alpha 1, beta 1, these are only differentiable parameters, otherwise there is no difference. If someone use beta 1, beta 2, beta 3, it is correct. If the other use alpha 1, alpha 2, alpha 3, gamma 1, lambda, whatsoever the reason is. So these are just notation, and when you will be going through the books, you will come to know that there is the change of notation. Some are using beta 1, beta 2, some are using beta from starting from beta 0 and beta 1. So never confuse yourself. So coming to the model of the Amna, and she estimated this model. And what happens? The other person say, I say that this is the person, that is the Ashraf. Now again my arrow can hit the target if your name is Ashraf, so I am happy, but unfortunately it is, if it is not, no need to worry about this. And the Ashraf comes with the model that this is the situation. He estimates this model. Look at this. Amna dropped one of the variable, that was x3 from her model, and Ashraf was so over efficient and he said no, he knows the theory very well, and he knows that there is only a linear relationship, these parameters are called the lambda. So starting from the true model, we traveled towards the Amna, and then we came towards the Ashraf, and we saw that this is the situation. Now how we come to know that this is the situation? So we will be getting the residual from all the three terms. From the first one, you can say that is, I again call this, that this is the person whose name is, you can say, the Balkis, randomly selecting nowadays. Balkis has a true model. So I would like to plot all these residual, and then I would like to show this, that how you come to know the model is correctly specified or there is misspecification. The utility, I am going to explain this on the next slide. The utility of examining the residual plot is thus clear. What is this clear? If you look at this, I will be, you can say, replicating this slide on the, this picture on the next, you can say, the empty slide. But here you can see that if there are specification errors, look at here, from here to here, this is for this model, you can say this is for Ashraf, and these residual plot is for, you can say, for Amna, and this is for Balkis. So what this means, as we are going towards the true model, starting from the Ashraf and going towards the Balkis, and we are looking that the residual plot is showing different trends. So if you see, we will see that they are showing different patterns. So let me explain this, and then I will come to know that what is the difference between this. So this is the first model, that is that I say that this is the true model. This is the 0, and this is the model of Balkis. Now I will write in Urdu. Just look at this. I say that these are the residual terms. These are the UI hats, and you have plotted it against, you can say, you have plotted it against the output. That is your X variable. So this is, as the output increasing, residual are fluctuating, but you can see there is a random trend. In the true model, the residuals cannot be predicted, they are going randomly. Now we come towards the Amna model, and if you see, this is showing, this has been taken from some of the data. Suppose that this is, and I say that this is the situation, and this is from the Amna model. And if we come to here, that this is Mr. Ashraf's model, and this is, we say that this is showing this trend. So look at this, this is Ashraf's model. So look at this, as we start from here to true model, the pattern of the residual is different from each other. Look at here, you can see there is a systematic trend. In this diagram, there is a systematic trend. Look at there, from here, if I say this is point A, this is point B, you can see there is the downward sloping. And if someone is at this point, I can easily predict that the next value will be lower. And if we start from B to C point, you can see that every time residual term is getting information from the previous residual term, and there is a positive relationship, and these are going up and up. Similarly, there is a pattern, but the pattern becomes a bit smaller in case of Amna. And if you look at the Balkis model, that we assumed Balkis should not be very happy that she fit the good model, but we assumed that she fit the good model. So this is the trend. If you look at the plot of the residual of your estimated residual, I assure you that if these are randomly scared, it is a very sigh of relief for you that you have estimated the model in a very proper way. If you come here, the same situation I have showed there. This was the first formal test, that was the plotting of the residual. The second is the Durbin-Watson statistics, very famous, and you can say you are well aware of this. But when you came to know this, we were talking about its relevance in the context of autocorrelation. So avoid confusion and look at this. Here we will be talking about this in the context of the specification. To use Durbin-Watson statistics for detecting the model specification error, how we proceed? From the assumed model, obtain the OLS. OLS estimate, what this means, set the model, apply the ordinary least square and estimate beta 1 hat, beta 2 hat, जितने भी आपके हैं उनको जो है वो आप estimate कर लें. If it is believed, now you believe, now it is up, if it is believed that the assumed model is misspecified, when you estimated, you assumed that there was something wrong, and you are now just getting that some variable you could not include, and supposed that the excluded relevant explanatory variable is Z. You suspect and you detected by chance that this is your outside model, that is the explanatory variable, that is Z model. So what will be doing? Now you have come to know that which is the Z model. Now order the residuals. You obtain from the OLS, order the residual in step 1 according to increasing values of Z. For example, Z is, this is Z 6, 8, 9, and you should also arrange the values of UI that it should keep on increasing as the values of the Z. Now you will be thinking about that, how you will come to know that what was the values of the Z. Now you have guessed that some variable was out of your model. So if you have guessed, spotted that which variable was your model, and you are going to test that whether it is important, integral part of your model, you should know its value and you should arrange. First, what we said, Durbin-Watson statistics in the context of model specification bias. First, take the model, run the OLS regression, obtain the residual, and now what they say, suspect that there is some variable that is missing in the data Z, and now arrange the values of Z and UI. First arrange the values of Z as these are increasing number, and similarly you should increase the values of the UI hat. Now here is the definition of Z, that Z variable could be one of the X variable included. जो आपने include किए हुए हैं उन्हीं में से आपने कोई समझा के excluded है, that could be, or it could be you can say the function of x2 or x3. What this means, the Z variable may be correlated with the x2 or x3. Now what is the third step? Compute the D statistics, Durbin-Watson statistic. I deliberately did not write the formula. Now you will have to go some previous lecture, the lecture of, you can say, the autocorrelation, and you will have to remember the formula. The formula will be same applied here, and we will be talking about then if the formula is the same, then how we detect the specification bias. From the residual thus ordered by the usual D formula. From these residual you will go to the formula, you will come to know that by these two series you will be able to find the D statistics. From the Durbin-Watson tables, now there is a table in your any of the, you can say, the statistical book, or you can say the quantitative technique books if it deals with the more critical issues of the statistics, like the, you can say, the probability of such kind of thing, or distribution, F distribution, T distribution, chi-square distribution, normal distribution, and whatsoever the here is. So if the, from the Durbin-Watson tables, if the D estimated, look at this, now I will call it that D calculated, that you calculated from the formula that I didn't write here. You calculated the D statistics from the here, and now you went to the table of Durbin-Watson statistics. You have the degree of freedom, I have not supposed here what is the degree of freedom, but when you will be working on your data, you will be knowing about the n number of observation and k the number of parameters, and you know the degree of freedom is simply the difference between the number of observation n minus the number of parameters k. So what is this? If the estimated or you can say the calculated d value is significant, then one can accept the hypothesis of model misspecification. Here there is something very special. Our null hypothesis is at this stage is, our null hypothesis is, look at this in Durbin's test, null hypothesis that model is not misspecified. What this means, that we have set the null hypothesis that the model is not misspecified. If it is rejected, the model is misspecified. If it is not rejected, then there is no problem. So never just look at this, that every time the rejection gives us a favorable result. Sometime rejection and sometime acceptance works the do. The tests are designed in such a way that most of the time they try to reject or reject the null hypothesis. So what will be doing you? For example, I say that our D calculated is equal to 10.5. This is just assumption, and I say you went to the table and that your critical D, it was 8.7. So what this says now, 10.5 is greater than 8.7. So you reject the null hypothesis and you are saying that the D statistics is significant. So if this is the significant, you can say the model is misspecified. So now you are trying to bring the evidence that the D statistics is not significant. So this is how we form the null and the alternate hypothesis. These are not necessarily that there is hard and fast rule, as I told you previously, that every time we are putting into some box and the solution is there. Many of the time we are changing the different tests are designed in such way that they make the null or the alternate hypothesis in such a way. So this was the specification test, and that was the Durbin-Watson statistics. The most celebrated test. This is very interesting and very critical for you, because many of the people first test this. What is the name of this test? This is Ramsey, the person who you can say formulated this test. And this is reset. Reset is the abbreviation, and what is the abbreviation? It is abbreviation for regression specific, RE regression, S specification, E error, and T for test. So this is Ramsey, it is generally called Ramsey reset test. So this is very important, critical, crucial, fundamental and important for you, because many of the people apply this test, and it is very simple to apply this. Although it is very simple for all the tests to apply, I am not sure that I will be giving you the eViews one lecture, but if I am able to do this, I will show you that how this happened with a small span of time. And if you are not getting feedback from me, you should do it on your own self, and you should go for the help of the eViews. So what is this? Assume that the cost function is linear in output. We assume that the cost function is linear. Again, assumption. I am sure that you will be raising your brows that every time in this phenomena I am starting with the assumption, because nobody knows what is the true model. Because if you know that is the true model, then what is the need of detection and remedial measure for this? So we just suppose that this is our true model, and if it and then we apply postmortem. If it passes all the tests, we say that the model is correctly specified. Otherwise, we say that there is some problem or misspecification. So what is this? We assume that this is the true model, and I can write in alphabetical form, beta form. I say that this is the y, that is the cost. It is beta 1, because you are now more familiar with beta 1 and beta 2. And I say that this is the x2i, plus ui. What this means that there is a linear relationship. I would like to show this, that this is the relationship. If this is the cost, this is the output, and you can say that this is the beta 1, that is the fixed cost. I am not teaching you the theory of cost. So this is the situation. There is a relationship. It is our assumption. What this? Plot the ui hat against the yi hat. Look at this. When you will apply OLS on this, you will come the yi hat values, and you have the yi also values from where you estimated this. Look at this. yi भी आपके पास था, xi भी था. Then you estimated the OLS, then you have yi hat values and yi. And from these two values, you can just calculate ui hat value. And when you calculate ui hat value and yi hat value, so plot these values against each other, and then see that what is interesting situation there. The residual in this figure show pattern. Look at this. We have taken, this is the ui hat, this is the yi hat, and this is the discontinuity, and I am now connecting this figure. So what is this? If you see that there is some specific trend of ui against yi, and which this means show a pattern in which their mean changes systematically with yi. Look at this, from here to here, mean value of this ui hat on the vertical axis, this changes according to the values of yi hat, and from here this point, for example this is C point, C to D point, you can see again as the y values are changing, the ui hat mean is also changing over time. This suggests, what this suggests? This suggests that if we introduce yi hat, this gives us a hint, you can say the indicator, you can say the positive point, that if we introduce yi hat, a new independent variable in some form as regressor. अब हमने यहाँ से चेक कर लिया कि yi hat और ui hat में कोई लिंक है. Now what we are doing, we are including yi hat as an independent variable, and in which form it is up to the researcher. You can add, you can introduce yi hat only, yi hat square, yi hat cube, it is up to you, and finally you will be looking at this. We introduce this, it should increase r square. Definitely, as we include a new variable, it increases the value of the r square. If r square is statistically significant, it means model was misspecified. If our new r square, that is, you can say that this was first, our r square will come from here, and when you will, I will be telling you, I will be showing it on the next slide, when we will be adding it yi hat as a regressor, then we will be getting some another yi hat that we will call the new r square. So we will be getting new r square, it will be increased over the previous one because a new variable has entered into our model. If r square is significant, I will tell you how to test its significance. If it is significant, the model is misspecified. Reject the null hypothesis. Again, the null hypothesis is model is not misspecified. Or in other words, you can say model is, it is a simple way, model is correctly specified. ये और आसान कर दिया. This is the null hypothesis, and as you will reject, there will be problem, and most of the time we reject of this. So what is this? If what I said that plot, this is the yi hat and this is the ui hat. So I say that this is the trend. So what is this? That with the changing values of the y, the mean of the ui from here to here and from here to here, it is changing systematically. So what this means? We introduce the yi as a regressor, and my model will become, this model will become yi hat is equal to beta 1 plus beta 2 x2I plus introduce yi hat as an independent variable. yi hat इसके साथ बीटा लगाना होगा, बीटा 3 yi hat plus if you want to take square of yi hat, it is up to you. If you are only satisfied that this is enough, it is up to you. I will be adding it beta 4 yi hat square plus ui. This is the situation. Now the new model is this one. Now what is this? When you estimated this model, you have some r square. Call this old r square. Old is gold. Old r square. And if this is the new r square. Every time when you estimate the regression, you know there is r square. What is r square? Coefficient of determination, that how much proportion of your dependent variable is being explained by the independent variable. So what is this procedure? How to proceed? Although I have explained, but look at this. First of all, run the OLS. Go to up, run the OLS on this as I have showed here. Take a model and assume that this was true model. This should be assumed. If you will not assume this, this may create some of the problem. So assume that this is the problem. This is the true model. Obtain the estimated yi hat and use estimated y as regressor. Give the name old and new to r square. Everything I have explained, so there will be only repetition, so I will be avoiding this. So this is your new model. If you look at my model, I think these are the similar. Look at here, these are the similar. Just we have introduced the yi hat as independent variable, yi hat as well as yi hat square. Now what is the formula of, again looking at this, f test is always nowadays in our discussion, and we are using it without giving any proper explanation. But I think by giving some small doses on different occasion, now you have to come to know that f test the significance of the parameters simultaneously and t test only one by one. F has also ability to test one by one. Use the f out whether rs square new is statistical significant. Now we are interested in its r square, because in the previous we have assumed that that was the true model. What is the formula? R square new है आपके पास value, r square old definite value, number of new regressor. If you look at this, we have introduced two new regressor, yi hat square, yi hat cube. If you have introduced only one new regressor, you will be writing here 1. If you have introduced 2, you will be writing 2, and so on. 1 minus r square new, again the same thing, and total number of observation and number of parameters, total parameters in the new model. If I limit myself on this, this is one parameter, 1, 2, 3 and 4. So this is the. Now what is the, at the end, how to decide? If the computed f value is significant, if you were sitting before me, I would have asked that what will be the, you will reject the null hypothesis. Every time when your calculated value becomes tabulated, you reject the null hypothesis. But the formulation of the null hypothesis is very critical. Look at what was the null hypothesis. Model is correctly specified. So you rejected this null hypothesis. So we will see that if the computed f value is significant, significant means f computed value is greater than f tabulated. There is a table of f distribution. You can easily get the value. If you have only the number of observation n, and you can go into the looking at the degrees of freedom, you can go to the f values and you can find that what is the f value. Now I have taken an example because this is the Ramsey test. I would like to again say that this is very critical test. So what is this? Suppose, if you remember, this was our first model. And you remember what we said it, that this is true model. इसी को हमने कह दिया कि that it was not specified now, that it was not correctly specified. Look at here only, if you remember, this was alpha 1 and this was alpha 2, and you know this is our cost and this is our output. So what is it? These are the standard errors. We are concerned about R square. This is now the old R square. What this means, this is the new regression. You added, look at this, yi hat square and yi hat cube, and these are its new variable, and the new R square is R square 0.99. So it is compatible with one of our previous finding, that as we increase the number of regressor, R square automatically increases. So if you remember, we said that while we are comparing two R square, the number of independent variable in both the model should be equal. So what is this? Is the new R square. So look at the formula. If you remember, R square new minus old. This is your new, this one, new R square. This is the old R square, you can see from here, and this is 2. What is 2? You can immediately go back. Number of new regressor. If you remember, you have just introduced this one regressor, yi hat square and yi cube square. These are 3. And what is this? 1 minus new R square. This is the very simple. And 10, I assume that the number of observation is 10. That is n is equal to 10. And the total number of parameter is, now look at here, this is the model. 1 parameter, 2 parameter, 3 parameter, and 4 parameter. So this is the calculated value of f that you have, and it is a very high. As it goes beyond 2 or 3 rule of thumb, it becomes significant. So what is this? I suppose that the f calculated is greater than f tabulated. No need to suppose, it is definitely greater than the f tabulated. So what is this? Your R square, your new R square. What this means? New R square is significant. Significant mean कि आपका नया R square significant है, तो इसका मतलब है कि नया मॉडल आपका जो है that is more reliable. So we reject the null hypothesis. What was null hypothesis? That our model is correctly specified. We reject and we say no, our model was not correctly specified, but the new model is, you can say, more reliable as compared to this. So this was the Ramsey reset test. You should be full command over this, and you should know that simply at the end you will be comparing the f values, and it is very easy to do this. The other well celebrated test is the Lagrange multiplier test, LM test. So Lagrange multiplier, if you are good aware of the mathematics, there is a Lagrangian multiplier, and the same person you can say the formulated this test. If you look at these model, I would like to give 2 names for these 2 model. If you look at this model, and if you look at this model, there is difference that on the right hand side there is a large number of independent variable, but on the left side there is only one independent variable, and the relationship is linear. Here the relationship is non-linear because the same variable is included as a square and the, you can say, the cubic cent. So I would call it the restricted variable. Restricted, not variable, restricted model. And I would like to call it unrestricted model. Unrestricted model. Why I am calling this? Because we are putting 2 restrictions, that xi square and xi cube are equal to 0. We are putting these 2 restrictions into this model. So where now these are 2 models, this is my starting point, and this is that one is, you can say, that is the restricted model, the other is unrestricted. This test is considered an alternative to Ramsey reset test. This is almost, you can see, the replication of the Ramsey reset test, and we will continue in this discussion, and at the end we will see that whether our results are according to the Ramsey reset test. This is an alternate, and you can say, but the Ramsey reset test is more celebrated, widely used and more preferable. But at the same time, if you go to this, the procedure is a bit different, and it is called, you can next to the Ramsey reset test. Estimate the restricted regression. If you remember, there we called that this was our true model. Now just there is a change of notation. Now I am saying that estimate the restricted model by OLS. Every time keep in mind, unless explained, we are in this discussion, we are talking about that we estimate OLS and you can say the autocorrelation and heteroscedasticity and the multicollinearity. We introduce the weighted, the generalized and the feasible least square, but first we mentioned that now we are going for these methods. Unless and until I do not make clear, I make not clear, you should immediately know that I am talking about the OLS. If in fact the unrestricted regression is the true regression, for example, if it is the true regression, the residual obtained in restricted model should be related to the squared and cubed output term, that is xi. And again, just another way to say the same thing, only the angle is changed, the target is the same. For example, Ramsey was trying to hit the target from 45 degree, and I can say the LM test, the Lagrange test, is going to hit the target from some other, you can say, the 60 end. What is this? It is assuming the Ramsey was saying that this is the true model. It is saying that this is the restricted model, and it's is saying the Lagrange multiplier test saying that if the restricted model is true, then the residual obtained from this should be related to these two values, xi square and xi3 square, because if it is true, it should be related to that. This suggests that now if it is related, now this suggests that we regress the obtained UI hat, यहाँ से आपको मिले थे जी पहले में OLS जब आपने अप्लाई किया. This suggests that we regress the obtained UI hat in step 1 on all the regressor. UI hat, we take UI hat, and what we are saying that now there is a suspicion of the link. We have identified the link between the UI hat, if it is a true model, related with the xi square and xi cube. So what this is, we now, if there is a link, we take it as dependent variable and we regress it on all the axes, xi, xi square and xi3. And sometimes I am using VI, just I got the, you can say I spotted this and I immediately came to know that I have to explain UI, error term, VI, these are the same thing. Error term, disturbance term, residual, whatsoever I am using, these are the similar thing, so you should not confuse. Where VI is the error term with usual properties, V properties that it is randomly randomly scattered. Now what is this? If you will get R square from here, if n R square, n means number of observation, R square follows the asymptotically in the large sample, follows the chi-square distribution, and we know that it follows the chi-square distribution. Now you will calculate the chi-square value of calculated chi-square value. आपको याद होगा कि यहाँ पर n 10 है, because we are working on the same data, and previously in Durbin-Watson statistic we assume that n is equal to 10. So this is, you can say that we apply this and we say that in the asymptotically the nr square follows the chi-square distribution. And as you know, there is in the regression it is dependent variable, it is the error term, so there is the appearance of the chi-square distribution. Now again you have to reject or accept the null hypothesis. Null hypothesis will remain the same. So help me to make the null hypothesis. So you are helping me. I supposing you are speaking that H naught is equal to the model is correctly specified. The most refined form, correctly specified. We are saying that the model is more correctly specified or specified. Now again you need not to worry about this. You know when to reject the null hypothesis and when to accept the null hypothesis, or you can say do not reject the null hypothesis. If the chi-square value in this way you will get obtained exceeds the critical chi-square value, there is a chi-square distribution table and you have number of observation. Against these number of observation there will be the value of chi-square. If this increases the critical value, for example the chi-square, I say the chi-square critical now and the calculated is greater than chi-square tabulated, then you will reject the null hypothesis. And what you are saying indirectly, that your model is misspecified. Go to your model. This looks that the model was, your restricted model was misspecified. Example, look at the example as we explained the scenario in case of the Durbin-Watson statistics. Restricted model, this was our restricted model, not new. Go to previous one, this model. So this was our restricted model. Look at here, we regressed the UI hat as a procedure, and look at this. We came up with regression. This is the standard error in parenthesis. This is the standard error of this. This is the R square, new R square. Here we have not reported the R square of this because in this we are not interested the new R square or the, you can say, the old R square. We are interested on the latest, or you can say that at the end we have calculated the R square. N R square, and you remember in the just previous 5 or 10 minute discussion, N is 10 there and R square, and you say the R square is here. So the value of the chi-square calculated statistics is equal to 9.86. So the chi-square value from the table is 9.21. When you go to the table against chi-square distribution against the n, that is the 10, you found that there is the value of 9.21. You should see the tables of the many of the books. Many means that if there are available. It doesn't mean that the table will differ from one to other. That this is I would like to take you in your matriculation age when you are aware of the logarithmic table. This is just similar to those tables, and this you should be expert, although the computer has the potential to put the true value and whatsoever, but at least you should have some manual, you can say, the practice of this. Now what is this? What has become, if this is chi-square, this is calculated, is now greater than this chi-square tabulated. In other words, I can write 9.896 is greater than 9.21. So what is this? Therefore, the observed value of 9.896 calculated is significant. As our calculated value becomes the statistics, we say that it is significant, and as it is significant, we reject the null hypothesis. And you have made, you have helped me to make the null hypothesis. I would not allow you to go to the previous slide. Just decide here, and you are deciding, what deciding? That the model is misspecified, because you are rejecting the null hypothesis, and your null hypothesis was the model is correctly specified. The conclusion would be the reject the restricted regression. The conclusion is similar to that of Ramsey reset test. If you look in the Ramsey reset test, we also rejected the null hypothesis, and we said that the model is misspecified. There we only, the change was, we said that this is the true model and the old new model. Here we are saying that this is the restricted model and this is the unrestricted model. This was our discussion about only one thing, that if model is underfitted. Overfitted में तो बिल्कुल ही मसला हल हो गया. That if I think if I will explain it here, I would like to explain it at later stage in the summary. If I explain here again, you will be mixing up the thing. So just we have completed our tests that were helping us to detect is there any underfitting. We have excluded some of the important variable mistakenly by laziness or by, you can say, वैसे ही हमने इसको जो है वो निकाल दिया. By now we assumed implicitly. Keep in mind, it is a very good way to good time to explain that when we are opening one of the loophole, we are keeping all the other loopholes closed. ये नहीं है कि हम Pandora box, we open the Pandora box and everything, we are just putting one chicken under the shed and the other is going out of the shed and then catching the other. We are just picking one chicken out of the, you can say, the under the wings of the, you can say, the hen. So this is, keep in mind, when we are talking about one thing, we are assuming that all the other things are you can say the constant are similar. By now we assumed implicitly that the dependent variable y and the explanatory variable x's are measured without any error. We talked about and kept on discussing, but we implicitly by assumption assumed that there is no measure of error in the variable of the y, that is the dependent, and variable that is the independent. In practice is empirical is different something from the theory. When you go into the field, you have different circumstances. This is the similar thing that when you watch a movie, it is full of action, and if you apply it into the bazaars, you will get the reverse result of this. You will not be hero, you will become a zero person, as the people will be beating you brutally, and you will be looking, your mind will come that there is a difference between the film and the reality, although it is a replication of the reality, but most of the times it is some of the rare cases. So I am not suggesting you that first watch the movie, then show your you can say the hero-ness to attract XYZ. It is, I am leaving the blank. So what is this? In practice it is not true. You assumed a very critical assumption. Every assumption is not in practically true, because if it is true, why we need to take assumption? So here we are saying that when we implicitly assumed that this is that y and x are correctly measured. Now I am not talking about the specification error, bias. I am talking about how you have measured. For example, if I am measuring the height of you people, if for example if your height is 5 feet 8 inches, I take it 7.5 inch, so there is measurement error, or I use some proxy for this. Whatsoever the reason is, there is a problem. In practice there are non-response error, and there are reporting error, there are computing error whatsoever. Whatever the reason is, measurement error आ गया आपके y या x variable में, error of measurement is a potentially troublesome problem. We are not concerned about from where the you can say the problem is coming. We are only concerned that if there is measurement error, there is a huge and potential problem. Now we will be talking about differently that when there is a measurement error in the dependent variable, and when there is a measurement error in the independent variable. It is just, you can say, you can divide this discussion as overfitting and underfitting. In some case you will see that there are very small consequences, and in some case there are very huge consequences. Let me know in which case the underfitting there are more consequences or overfitting. In underfitting there were more consequences, and now we will see कि y में problem आ जाए, is it more dangerous, or if there is problem in the independent variable, or this is more dangerous. It still, if error in the measurement of dependent variable, that is the y variable, what will happen? It still gives the unbiased estimate of the parameter and their variance. No problem. Everything is okay. So if your dependent variable is, it is not, I am not suggesting that take your dependent variable carelessly. But I am saying that if you have made two mistakes, one is less costly and the other is more costly, although the mistake is always mistake, you will have to be penalized for this. However, the estimated variance are now larger than in the case where there are no such error of measurement. First you take, there is no error in y, you measure OLS, and then you take, there is measure of error in the y. You will see there is a very small difference, that only the variances will become larger, and you know what are its consequences. And if there is measurement of error in your independent variable, this could be very costly. It is now, can you tell me, is it compatible with the underfitting or overfitting? Just think about, and I will not wait, I will tell you that this is related to the underfitting. Error in y is like the overfitting of the model. Error in x variable, it is like the underfitting, and we should be very, very careful about this. Measurement error in explanatory variable pose a serious problem. In the measurement error in the dependent variable doesn't pose a very, very serious problem. The consistent estimates of the parameter become impossible. OLS estimators are now not, you can say, the consistent. They have become inconsistent. मैं नहीं बताऊंगा कि what is consistent or non-consistent. This may be the 100th time you are looking at me that I should explain. So now I am not going to explain this. However, as we know, if they are present only in the dependent variable, now I am going back, the estimator remained unbiased. Look at this. This is y, this is x. Write this measurement error in ME, measurement error in y, measurement error in x. Here, look at this. Their results are unbiased. Here biased, here inconsistent, consistent, here inconsistent. So this is the issue at this stage. So rather than going further, that explaining some of the other criteria, I would like to wind up the lecture, and I would like to give you the summary of the today lecture. As usual, what we started, if you remember that the exact round about 60 minutes before, we started the detection of the specification bias, and we started from the formal methods. The first formal method was that the residual plot, that we apply the OLS, we assume that some model was the true model, we exclude one variable, then we exclude the other variable. I would like to say that you should remember that I use the name of Amna, Ashraf and Balkis at that stage. So what is this situation, that if residual plots are showing random effect, they are scattered randomly and you are plotting them against the independent variable, that is the x. If they show the random effect, you can say that there is no problem in the model. But if there is some problem in the model, in the residual term, you should immediately think about that there is problem. The error should not show any of the consistent result. Then if you remember, we came towards the D statistics, Durbin-Watson statistic, very familiar, very easy. This is another test of this. This just assumes, if I think you remember, that we calculate the D statistics from the usual formula. and this time today I did not provide you the formula. You may be curious about this. If you are so curious, go to the formula and remember it by heart. It is very, very important. So what is this? The D statistics we calculated. I am not going to explain that how we calculated this, how we did this, that or that. The only difference, first we said that this is the true model, and then we suppose that the other was not the true model, and we kept on capitalizing this situation. If the D statistics is significant, your model is misspecified. You reject the null hypothesis. I am just explaining it only one time, and in the next text that I am going to give you in the summary, I will not be telling about this. Our null hypothesis that our model is correctly specified, and when we will reject this, we will see and say that the model is our result will be the model is misspecified. Then we just jump towards the Ramsey reset regression specification error test. Very celebrated, very easy test, in which we started from the true model, and we said that is not the true model, and at the end, you remember, we came across the new R square or the old R square, and we tested it by the F test, and we concluded that if F test, the calculated F test is the value of the calculated F is greater than the tabulated F, we reject the null hypothesis in the Ramsey reset test. Then there was an alternate towards the Ramsey reset test, that was the LM Lagrange multiplier test. This is just, you can say, the alternate, or you can say the similar as compared to the Ramsey reset test. Here we started from the restricted and the unrestricted model, and after some time we got the residual, and we again regressed the residual on the x2 and all the independent variable, and we talked about the chi-square distribution, and we said that nr square follows the chi-square distribution, and if the chi-square distribution calculated value becomes greater than the tabulated value of the chi-square, we again reject the null hypothesis. I also presented the sum of the example. After this, we came across the measurement error. In the last our whole discussion, we just implicitly assumed that our x and y variable, there is in the x and y variable, there is no measurement error. But if there is measurement error, it creates many problems. So what we said, we bifurcated our discussion into two groups. First, we saw that if there is a measurement in our dependent variable, we were lucky that there were not many, you can say, the dangerous consequences of this. And on the other hand, when we studied that if there is measurement error in the independent variable, we came to know that there are very huge repercussions of this. So this the error in the independent variable is similar to the underfitting of the model, and error in the dependent similar towards the overfitting of the model. So at this time, when I say that in this side there is less dangerous and that side more dangerous, I am not saying that you should use the less dangerous. I am using that you should go to the true model, and you can only hit the true model if you know the true theory and empirical knowledge about this. If you are unaware of this, these tests will help you to specify where there is a problem, but ultimately the only theory has the you can say the pivotal role in specifying the model. So see you in the next lecture. We will continue our this discussion. So until that, take care and Allah Hafiz.